Good evening, class. Thank you very much for coming to this last talk of the day. I hope you'll find it interesting, fun, but also hope you'll learn some stuff. The aim of this is not just to talk about Star Wars and Lego, although I will be talking about Star Wars and Lego. So I'll start off by giving you some background as to what led to me putting this talk together. So I actually put this together about the first version of this about a decade ago. And it was as a result of doing I worked for a consultancy, we did some work for Lego many years ago. And as a thank you, they sent us a number of big Lego sets, right? The sort of ultimate collector's edition Lego sets. And so one Christmas, we got together in the office. We were on the bench, or beach, we call it in ThoughtWorks. And we sort of got together and built this Lego set. And so I put this talk together about the process because, you know, there was, I don't know, 5 or 6 people. We each had like a decade or more, maybe a lot more agile experience. We're working on agile teams. And it was interesting how the process evolved of us building this Lego set. So I'll talk through that in a bit. But then, I guess my interest, I'm a software developer, my interest in software development and the sort of ecosystem around software development has changed over a number of years. And I've become very interested in the intersection of software architecture, organizational design, and specifically how we optimize our organizations for the flow of work. So then, a year or so ago, I put some of that thinking back into this talk. So it's really my journey over the last 10 years from a much more junior, much less grey software developer to a much greyer, more experienced software developer. So that's really what this talk is about. It's about my journey. It's about Lego. It's about Star Wars. So I'll give you a brief note on ThoughtWorks first off. So ThoughtWorks is a big software consultancy. That's all I'm going to say about it. It's going to be that brief because we don't do sales, right? So brief note on ThoughtWorks. Lego, I'll do a brief introduction to what Lego is, just in case people in the room don't know what Lego is. I'll do a brief introduction to Star Wars, presumably to some people who haven't seen it. There's always one awkward person in the room who's never seen Star Wars. They always put their hands up. And then I'll do a brief intro to Flow. And then I'll tell the story of how we built the Millennium Falcon. So first of all, a recap on Lego. Does anyone in the room not know what Lego is? I can't really see, but everyone knows what Lego is. Good. That's it then. I'll just move on. So a recap on Star Wars. I might go into a bit more detail here because some people have seen the films, some people haven't seen the films. So episodes 1 to 3, we don't talk about episodes 1 to 3 if you're into Star Wars. So we'll just move over that. Go on to episode 4. Episode 4, this is a quick summary. Boy realizes he can do magic, falls in love with a girl, sticks it to the evil empire. Ben, no, not Ben. Ben dies if you haven't seen it. Spoiler alert. Episode 5, boy's mate gets frozen. Boy learns how to do magic, finds out his dad runs the evil empire. This is getting awkward for the boy at this point, right? Not just he's fallen in love with a girl, but now his dad's running the evil empire. But it turns out, actually, it's his sister he's fallen in love with. This is getting even more awkward for him. I'm going to take a moment here. I actually went, in case you doubt my geek credentials, right? I actually went this weekend to the Royal Albert Hall in London, which is the equivalent of this, I guess, this venue we're in now, to watch Return of the Jedi in concert. So it was a giant cinema screen and a 100-piece orchestra playing the soundtrack. It was astonishing. I can recommend doing that if you can. So episode 7, the new movies. Okay, this slash S boy slash girl, whatever. Girl realizes she can do magic, falls in love with a boy, sticks it to the evil empire. Han, no, not Han. Episode 8, the boy from 4, 5, and 6 is back. For some reason, he's old and grumpy, and he drinks puffin juice. It's a bit weird. Blah, 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 Leia, not Leia. And then finally, episode 9. Wait, what? There was a guy who was dead in Return of the Jedi, and now he's back? Weird, and he's got all these ships, and I'm all the Jedi, whatever. That's Star Wars. Are we good with Star Wars? Okay, good. That's my summary of Star Wars, all clear. My recap on Flow. I'm going to give you my definition of what flow is, which is this: system optimization to keep stuff moving. Now, your definition may vary. That's my definition. But what do I mean by stuff? I'll unpack stuff. Stuff can be anything, right? Stuff can be physical goods. The flow of physical goods, from being oranges picked in Sevilla to being sold to you in a supermarket via just-in-time supply chains, right? That's an obvious example of flow of goods. And we spend a lot of, our colleagues in businesses spend a lot of time optimizing the flow of physical stuff through warehouses and into shops and so on. But it can also be information, the flow of information, right? And if you think about what we do as software developers or people involved in technology, product owners, project managers, analysts, etc., we're concentrating on the flow of information, right? The flow of ideas from someone coming up with an idea through a number of different value-adding activities, technical term from the lean world, through to, say, being put into production, where our customers hopefully say, thank you. Daniel Terhorst North has got a lovely description of what the aim of what a team should do, a product team should do. And they should work to safely and sustainably reduce the lead time to thank you. That's the aim of our teams, essentially. But the stuff that's flowing through our teams is information. And if you think about it, it goes from one state, it gets enriched into another state, and then flows through to a developer who's going to write some code. That information gets transcribed and deployed. But it's just stuff, the flow of stuff. And what we're trying to do is optimize that flow of stuff in order to make more money, save lives, or do whatever it is. Again, I'm a bit of a geek. So my name's James. I've been a software developer more years than I can remember. I've been working for ThoughtWorks nearly 17 years now, so I'm kind of grandfathered into the whole the company at this point. And this is some work I've been doing recently with some colleagues on patterns of legacy displacement, which you can go and find on Martin Fowler's website. We thought it was about time some people took a real sort of serious look at the patterns you can use to actually displace things like mainframes or big older systems. Because normally when you ask about how you're going to do that, people say, oh, we use the strangler vine, and that's it. Right? There's much more to it. So we've written a bunch of patterns. Hopefully it'll turn into a book. Furthering my geek credentials, not just Star Wars on Lego, I'm into, this is me and my son at Warhammer World in Nottingham. I'm also an avid Warhammer 40,000 gamer, so there you go. Now, it's time to witness the firepower of this fully operational conference talk. Well, it was an office. It wasn't a galaxy, to be fair. It was a long time ago in an office far, far away. Lean Lego. I should have the music there. Ta-da! Episode 4. A new box. So this is what turned up in London. This is the old Ultimate Collector's Edition one. At the time, it was the biggest Lego set Lego had ever made. The Millennium Falcon. It's a 16-plus guideline for building this thing, right? So, you know, you've got to be quite, I guess, good at Lego by this point to be able to tackle something like this. This has got 300 double-sided pages in the manual, and it's quite thick. It's like this thick. And at the time, over 5,000 pieces, which was, again, it was the biggest set they'd ever produced. And it was all kind of, you know, in this box. We open this box, and there's this team of people. There's some developers and an analyst knocking around on the beach, and we thought, right, we're going to start building this thing at Christmas. How long can it possibly take? All right, because we've got a week or so before Christmas in the office. Let's start building this thing. Well, that's the start of the story. I am going to actually try and give you some actual information, useful stuff you can take away with you as well. So I'm going to talk a little bit about some tools you can use for measuring and monitoring flow and optimizing flow. And then we'll use these tools throughout the course of the story. And these will probably go from, yes, we've all seen that, to some that are a little bit more esoteric. So presumably, people in the room have come across story walls, Kanban boards. We use them virtually now often. I still, you know, I have a physical wall in my office at home, which I have my Post-it notes or index cards on. But essentially, it's a way of tracking work, right? It's a way of visualizing work so that everyone in the team knows what's going on. Our stakeholders understand where we are, and we know what we're going to be doing next. Story walls tend to have a number of different features. You know, they tend to have these swim lanes. They range from the simple, you know, sort of, doing done, through to the much more complex ones around things like, you know, Kanban processes where you have ready for development states and ready for testing states, and so on. In this case, we've got one which has got a ready for development queue. I'm presuming people in the room are familiar with storyboards, so I won't talk much more about that. The next thing I'm going to sort of talk about briefly is a burn-up chart. And again, 101 stuff, right? Scrum tends to use burn down. ThoughtWorks, over the years, we've tended to use burn up. The reason we use burn up is because, as you can see in this one, he says, gingerly moving forwards like that, with lasers. As you can see, turns out scope, which is this blue line, tends to increase over time. I've not really seen many projects where the total scope comes down over time. So burning up to your total scope seems to us a more sensible way of doing things. But this is also showing another couple of things as well. So the light blue line is actuals, right? So that's what we've actually delivered. This is from a real project I was on. This is the actual number of story points we've been delivering. And then you've got the red dotted line, which is the prediction for when we're going to finish, when we're going to hit total scope, right? And that prediction is based on, I'm sure you've heard the phrase, yesterday's weather, right? So this is very common in agile planning. You base your prediction for the future on yesterday's weather, on the basis that, you know, today's weather is going to be the same as yesterday's 70% of the time. So you take what you've done previously, you predict that into the future, and you get when you're going to finish. Burn-up charts, all very good, right? Simple. But this is where it starts to get more interesting, I think, when you start to look at things like cumulative flow charts. Now, who in the room has come across cumulative flow charts before? Got 1 or 2, 3 hands or so, 4 hands, 5 hands, something like that. So cumulative flow chart is a way of tracking not just your total burn-up, you know, when am I going to be finished, when's the entire thing going to be finished, but it's a way of, in a fine-grained way, tracking each stage of the development process in order to be able to identify blockers. I'll show you some examples of this in the real world in a minute. But what we can see in here is at the front of the flowchart, you've got arrivals, so work that's coming into the system, whether that's, you know, a BA writing a new user story and it arrives in that queue, or whether or whether it's a developer finishes some code and it going into testing. You've then got departures at the other end, which is when, you know, the next stage of the process kicks in. And you can tell some really interesting things just by looking at cumulative flowcharts. You can understand where blockages in your development process are. Because that shaded area, which is the queue itself, right, that shows you the number of things you've got waiting to be done. So the stuff that's waiting for the next stage of the process. And you've also got how long those things have been sitting there in the queue. And this is an example, again, from a software project. And what we can see here is if you track those swim lanes on your Kanban board, but track them on a cumulative flow diagram instead of just a burn-up chart, you get to see more interesting things, richer information, which allows you to take action back to improving flow again. So what we can see here is that green shaded bit in this cumulative flow chart. That's stuff that's been signed off, but is waiting to be showcased, right? It's stuff that's just sitting there, done, right? The developers have finished, it's been tested, it's just sitting there. Someone needs to have a look at it and say yes. But in the meantime, it's just sitting there not doing anything, right? It's not earning you money, right? What you want to be doing, again, is optimizing for flow, optimizing for these things to be moving through the process as smoothly as possible. And similarly, in the pink shaded area, you've got this idea of it's showcased, but it's waiting to go into deployment, right? Waiting to be deployed. A bunch of stuff that's sitting, waiting to be deployed, is basically you just not making as much money as you could be making, right? Because each of those things that's waiting to be deployed, if it's been deployed, it should be making you money. So that's cumulative flow charts. You can start to use these, as I say, really, really simple. Most software will do, any of the Atlassian tools and so on will show you this kind of thing. The next thing is value stream maps. So who uses value stream maps? One person in the room, I see. So this is actually fascinating to me, because this is one of my go-to tools. And it might just be because I'm a consultant, it's one of those things that's in my toolbox. But for me, they're one of the most useful tools to understand the system that we're working in, right? Value stream maps come from Lean, essentially, from lean manufacturing originally. And the idea is you plot how long things are taking. And you separate things out into value-adding activities, which is the up bit, if you like, or waiting times, or non-value-adding activities, which is the troughs. So what can we see on this value stream map? This is showing 3 activities that take place sequentially. That might be analysis, it might be then followed by development, followed by deployment, right? 3 consecutive activities. In the first case, the analysis is taking 3 days to do. But then it sits waiting, doing nothing, for 10 whole days before a developer picks that up, right, and does some work on it, which takes 1.5 days. It then sits there waiting to be deployed for a further 30 days, for a whole month sitting waiting to be deployed, before finally it takes half a day to be put into production. And there are some technical terms associated with these. So you've got this idea of value creating time or cycle time of the individual activity. How long on average does it take devs to finish a user story? How long on average does it take to do some analysis and create a user story? You then got the idea of wait time. So stuff is spent sitting around waiting for, basically waiting for the next activity to happen. And when you look at things like just-in-time supply chains, what you'll see is they optimize away wait times. Because what you're saying with wait times, when you've got a bunch of stuff sitting around not doing anything, that's called holding inventory, right? And the whole point about just-in-time supply is you don't hold inventory, because inventory is basically cash, translates directly to cash. It's the same for what we do. It's the same with knowledge work. Holding inventory in big queues of work, waiting before deployment or waiting before waiting for code to be written to satisfy the requirements, is basically risky, right? Because requirements change, you know? It's stuff that's costing you money by sitting there doing nothing. And then you have the concept of production lead time, which is the overall time it takes to go from concept to cache. Now, honestly, this is the most useful, one of the most useful tools I've used to understand team structures, understand how path to production works, and so on. And they're really easy to create as well. That's obviously an example with the numbers on it. So in this case, it's, what does it say? Total wait time is 42 days. Value adding time is 5 days. Production lead time is 47 days. But you're actually only doing value adding activities for a fraction of the amount of time it takes to get something from concept into production. And you think this is from a real organization. Actually, I sort of borrowed and simplified a version of their value stream. It was a simple one. This is from a larger organization, very large retailer I work with quite a lot, or worked with quite a lot. And as you can see, as you start to build these value streams in bigger organizations, often you end up with these enormous, enormous, enormous value streams. And people say, oh, it takes ages to get anything done around here. Oh, but I can do my job really quickly, but it takes ages to get anything done. And then you look at the overall value stream and you think, well, that's why nothing gets done, right? Because it takes potentially years to go through these whole value streams. I should point out, I'm going to get my laser again, that, oh, can you see that blue thing there, I hope? That is writing code. That's it. All the rest of it is ceremony around creating requirements, creating options, asking architects to approve things, change request boards, and then all the way down this end, this is all systems integration testing, regression testing, exceptions testing, and so on. You build up these processes over time, of course. The next thing, and this is another one that many folk don't tend to use or see much of, I don't tend to see much of it, is the idea of using control charts. So I'm sure we've come across the idea of the methodology Six Sigma, which is lean optimization. It was very popular a decade or 15 years ago or so. And Six Sigma actually gets its name from control charts. So what a control chart does is it plots essentially your velocity, if you're doing it in story points or whatever, or how much stuff you're doing on a week-by-week or iteration-by-iteration basis. And then that's what the average line, that's what the spiky line is, essentially. And then you've got the average of how much we're getting done over time. So say, for example, 1 week my team is doing 30 points, the next week it does I don't know, 28 points. The next week it does 34 points. You've got this kind of spiky, variable amount that you're delivering every week. What control charts do is say, if you go 3 standard deviations either side of that, 3 sigmas either side, that's your natural variability within the system that you're working. Your team should expect to have that variability. Every system is variable to an extent. And what the upper and the lower control limits say is, if suddenly you only do 3 points, you should probably go and have a look, because it's outside 3 standard deviations from the mean. If you suddenly do 45 points, you should work out why. Why did it go so well that week? Because it's outside the upper control limit. But if it's within those control limits, that's just the normal variation that you have on your project. So control charts. Again, not something that I tend to see many organizations using. So fine, right? All very well, boring, sciencey stuff about monitoring flow. Let's get back to Lego and Star Wars. Episode 5, the Lego Strikes Back. So, you know, the first thing we did is we opened the box, we looked at the first page of the instructions, and we all just sort of piled into the boxes like Lego flying everywhere, woo, having a great time. So we also got all the stuff from the first page, and then we all sort of started putting it all together. And then we carried on, all getting stuff in the box, all putting stuff together, all getting stuff in the box, all putting stuff together. And it went really, really slowly. Right, really, really slowly. It took ages to get anything done. See, you can see, because we show you the nice value stream of the Lego system of work. This is what happens when you're building Lego, right? You're finding pieces and you're putting pieces together. That's pretty much it, right? And what was happening, it was taking a really long time to find stuff. A really, really long time. In this case, it was taking, I'm saying 10 minutes on average. That brings me to my first tip. Understand the system of work that you're working in. Understand the team, the system that the team is working in. Not just your team, but maybe one team out as well. And visualize that system using tools like value stream maps. And what we understood when we sort of thought about it a bit, what was happening is we were processing our work kind of serially. So we were finding bits and then assembling bits. We were finding bits and then assembling bits. And that's my second tip, is use things like Kanban boards to visualize the flow of work through your system, to visualize different states within your system. And the result of all this, well, on our burn-up chart, it was a bit sad. End of day 1, it was looking like the heat death of the universe before we were going to finish. Now, being a consultant, I can probably get away with sitting on the bench for 2 weeks before Christmas, but I probably need to go and earn some money before the heat death of the universe. So this was not looking good from the perspective of finishing this project. In fact, you can tell how old this presentation is because it's before memes. Back when we only had emoticons, yes, so sad face. Episode 6, The Return of the Process Jedis. So a funny thing happened next. We moved from the sort of system that we were using at the time, so this idea of, everyone finding a bit, essentially, everyone finding a bit followed by everyone assembling bits, moved from that model of working to a different model, where we had some people finding bits and some people putting bits together, kind of at the same time. So we sort of separated out the work into, just sort of naturally happened that we separated out the work and we ended up with specialists. Fundamentally, what we did, sort of intrinsically, intuitively, is we identified that there was this constraint in the system. This constraint, which is it was taking a long time to find bits. And we started doing things in parallel. It turns out you can find lots of bits at once. You don't have to concentrate on just the next bit on the Lego, on the manual. You can find the next bit, and the next bit after that, and the next bit after that at the same time. And that's what we did. So that's my third tip, is this idea of the theory of constraints. Now, I know there's been a more modern version called the Phoenix Project, but the original book that the theory of constraints came from was called The Goal, or is called The Goal, by a management consultant called Eli Goldratt. I'm not sure if you've come across The Goal. The Goal is it's a brilliant book. It's a business fable, if you like. It tells the story of sort of a manager of a manufacturing plant. And in that manufacturing plant, things aren't going very well. And he gets promoted and he gets told, unless we improve the situation, we're going to have to close the plant and everyone's going to be fired. And then he sort of has a beer in a bar to drown his sorrows and starts talking to some guy. And that guy turns out to be like a sort of a consultant wizard type person with a red sports car. And this consultant wizard guy, he starts to sort of give him information about how he might optimize the process within the manufacturing plant. And that comes out as this idea of the theory of constraints. So what is the theory of constraints? The theory of constraints says in any system, you're always going to have bottlenecks. Always. There will always be something that's going more slowly than other parts of the system. So in manufacturing, you're going to have many machines in a production line. Right? One of those machines will be the bottleneck, or one set of machines will be the bottleneck. In knowledge work, it's the same. Right? There will always be a bottleneck in our development workflows, in our development environments, right? Maybe you haven't got enough developers. Maybe stuff gets stuck in testing because we haven't got enough QAs to churn through to do the exploratory testing fast enough. Maybe we haven't got enough analysts to provide user stories for the developers to work on. The idea of the theory of constraints is you first of all identify where the bottleneck is. And then you work to minimize the impact of that bottleneck. There's 4 distinct steps, but that's fundamentally it. Look to identify the constraint, identify the bottleneck, and work to remove the bottleneck as far as you can. But the problem with the theory of constraints, or the problem with any system, is that the bottleneck then just moves. So you then have to repeat the process. Once you've solved one part of the one problem, you then move on to the next bottleneck, and the next bottleneck, and the next bottleneck. And this, in the Goal, it turns out to be what management is. Management should be about doing this. It should be about identifying where in our system of work we've got bottlenecks and working to minimize those bottlenecks, and then moving on to the next one, and moving on to the next one. Eli Goldratt he has a lovely illustration of the theory of constraints. He talks about scouts. I presume there's a scouting movement in Norway. Yeah, I've got nods, good. And he uses the example of going on a hike with a bunch of scouts, and some of them are fitter than others, and one of them is desperately unfit, and has got loads of stuff, carrying loads of stuff. And the idea is, this poor scout is slowing everyone down. So, the scoutmaster identifies this bottleneck. It's this poor, unfit scout, and he, takes a lot of his kit off, gives it to all the other scouts, and then that scout gets to move faster. You identify the constraint, you elevate it in the language of theory of constraints, and then you move on. On the basis that then all the scouts will get to their campsite at the same time. So the next thing is this idea of queuing and queuing theory. So interesting thing happened when we started finding bits in parallel. We kind of started piling up these little Lego bits onto the manual, onto the pages of the manual. Okay, so we've got all the bits we need for this particular stage. Let's move on to the next one. Pile all the next bits onto the next stage. Essentially, we started introducing a queued state, or visualizing a queued state, which was pieces that were ready for assembly. They'd been found, they were ready for assembly, right, based on, essentially, the pages in the manual. And then the folks who were putting the Lego set together, they could just pick pieces from the next stage of the queue. Right? So the folks assembling pulled from the queue, and the folks finding bits pushed into the queue. And that's a crucial thing in terms of what we do as well, right? Because we often hear about, okay, well, I can't do anything because I haven't got any. The testers are flat out. There's loads of work for them to do, so I'm not going to. There's no point in me doing any development because it'll wait for a long time waiting to be tested. And when we talk about swarming upstream in terms of on teams, this is what we mean. We swarm upstream and help by pulling work from the queue upstream. So identifying queues in your system helps control cycle time. I'm going to do a little sidebar now, because there's a really set of interesting facts around queuing theory, and how that relates to what we do. I read a book 15 years ago called The Principles of Product Development Flow by a guy called Don Reinertsen, who's an interesting guy. He's a former NATO nuclear submarine commander, ended up as a as a consultant, and he wrote this book about essentially knowledge work and how flow economics, or the economics of what we do, basically impacts our ability to get stuff done. And one of the things he talks about in that is this idea of queue size versus cycle time. I'm going to illustrate this idea with conferences. So this doesn't actually apply to NDC, interestingly. And you'll see why in a minute, I hope. So if we think about when you're at a normal, just a general conference, right, and you want to get some lunch, right? Lunch is going to be served at 1 o'clock in the afternoon, right? So lunch is served at 1 o'clock. And at 1 o'clock, the session finishes, and everyone leaves the session and joins the lunch queue, right? So if you can see at like 10 past 1, you go from a normal set of people who are just wandering in, getting lunch. Suddenly there's a massive jump, a massive number of people leaving a session, and they all turn up at the lunch queue at once. Right? You've got hungry people. That's your arrival queue. You then got fed people, right? And the rate at which people can be fed normally in conferences is fixed. You've got a constant rate of people handing out food, or a constant number of people around a buffet table or whatever taking food out. So you've got this constant rate of departures from your queue, if you like. So at this point, the session's finished, and you've got this giant queue waiting to get lunch. So just after 1:10, 1:11, you get this big increase in the queue size. The queue size goes from, say, 20 to 300 people. The question is, when do you know that this is a problem? If you're a conference organizer, how can you predict or understand as soon as possible that you've got a problem with queues, you've got a problem with hungry people getting angry, right? If you look at the cycle time, if you look at how long it's going to take someone to get served in that massive queue, they won't get served potentially until 20 minutes later. Right? If you measure cycle time, how quickly work is progressing through your system, it takes you a long time to understand you've got a problem. But if you just monitor queue depth, essentially, I'm going to go through that again. If you just monitor the depth of the queue, immediately, 20 minutes earlier, you know that there's an issue and you can bring lots of people in to help. This is essentially what you do in supermarkets, right? This is when you've got like only a few tills open in a supermarket, and suddenly the queue starts to increase. They don't wait and measure how long it's going to take you to get to the front of the queue. They just look at how deep the queue is, how many people are just queuing, and then they open more tills. So for what we do, it's much better to understand how much work we've got waiting in queues than to measure how long it's going to take. It's going to give you much earlier signals in terms of whether your your system is failing. You're suffering in queuing theory is called a catastrophic collapse, which is a nice phrase. You can understand that much more quickly by monitoring queues rather than monitoring cycle time. The question is, why is it different for NDC? Well, the difference with NDC is they spread the arrivals out over the entire day because there's food on all day. So you don't have this fixed point where everyone turns up and is hungry. People are just coming over the entire day and getting fed. So you avoid this problem entirely. It's very, very smart. Anyway, by doing all this, we got faster, right? That's fundamentally it. You can see we're now measured in hours to completion, which is good. That's my next tip. Use burn-up charts and yesterday's weather to track progress. If I go back to that burn-up chart, what we're saying here is, over a number of hours, we got so many pieces, so many bits assembled. When do we think in the future we're going to finish the whole thing, given there's 7,000 steps or whatever to do? At the beginning of the project, or the beginning of any process, you don't really know how long things are going to take. We estimate how long, I think that we've got we'll do 7 points per week or whatever it is per developer, times by 4 developers, we'll get 28 points per. And then we sort of say, that's how long our project's going to take, or our product build is going to take. But we don't actually know until we've actually done some of the work. And that's the idea behind yesterday's weather. Do some work, and then you can look at how long you're actually going to take, as opposed to just guessing at the start. So use burn-up charts and yesterday's weather to track progress. But it didn't stop there. some other funny things started happening. We ended up with T-shaped people, right? Come across this idea of generalizing specialists, the idea that, yes, you need people who are experts in a particular thing, but can also do, cover off some other roles as well, maybe. I would say, an expert in things like distributed system design, back-end development. That's where I wrote the whole microservices thing many years ago. That's where my deep expertise is. But I can probably do some JavaScript if you hold a gun to my head, which is pretty much what you'd have to do, to be honest. This idea of generalizing specialists. Similarly, I'm not a business analyst, right? But I could, not to the same degree, and I'm not going to do it as fast or as expertly, but I can probably write some user stories if I need to. I can probably do some exploratory testing. My brain doesn't work the same way as a really good QA, right? By which I mean the sort of person who, and this was a real bug on one project, someone raised a bug which was, if you put more than 32,000 characters into the password field, you get a 500 error, which is in Java land. I mean, that takes a particular brain, right, to work through the problem to that extent. But I can do some testing, right? I can cover off some testing. This is what we mean about T-shaping. And this is what we ended up having. We had a bunch of specialists who were really good at putting the Lego together, and a bunch of people who were really good at finding bits. And I guess that's kind of obvious in the end, right? Because when you were looking for things, if you're just doing that the whole time, then you get to, oh, I saw that bit a minute ago, it was over there, right, I can find it more quickly. Or if you're putting this thing together, and it's a big old Lego set, it's quite a sort of hard topological problem in a sense, right? You started to be able to see how that was going to change as you added more bits. So people started specializing. And these specialists noted this. And this is back to our control chart, right? Essentially, there was almost completely randomness. There was a randomness to the amount of time it took to find anything, or it seemed to be random. We had this massive variability in the system of finding pieces, which is kind of strange. And again, what you want to be doing with control charts is looking to reduce your variability, looking to make the system of work more consistent, less variable over time, more predictable. And it turns out that finding a piece basically is a function of the size of the piece and the number of those pieces that you've got. So if you've got lots of really big bits, you're going to find it really quickly. If you've got one really small bit in 5,000, it's going to take you a while to trawl through it, right? Basically, tiny bits, fewer of them take longer to find than big bits when there's more of them. So we ended up, just-in-time optimizing. We ended up with a little sort of system of just-in-time inventory that, we might need this in a minute, or I think I've seen this is a bit I haven't seen many of. Let's put it in a little pot so we know where it is. We can find it in the future. And at the end, essentially, we ended up with reduced variability in the system. So there you go. That's my next tip. Use control charts to understand the system that you're in and identify variability in that system, and then work to minimize that variability because that improves predictability of the process. Other fun things happening in our process as well. The first one was defect tracking. So this is a real defect bug card from this process of building the Millennium Falcon. We had two types of bug. The first type of bug was like and-on chord stop the line defect, right, which was a structural problem. We can't go any further because we need this bit, and we can't move on to the next bit until we find it. At which point, and-on chord stop the line, and everyone just started looking for the bit, right? So we found it and moved on. We then had another type of defect, which was a cosmetic defect, if you like, which we could carry on with the build, but we wanted to track that there was a bit missing. It might not look so great. We were essentially accruing technical debt, or Lego debt at that point. So we had these bugs. We also had this idea of, you might have come across this from Lean as well, is work in progress limits. So limiting the amount of work that you accept into a queue or you accept into a development state. So if there's 4 people writing code, you might only accept 4 cards into the being developed state, right? And the reason you do that is because if you accept more, you're going to be context switching, which is going to be a nightmare. But also, it forces the issue of understanding where the blockers are upstream. It forces you to look and understand where you can go to optimize. So that's what we did. We created work in progress. Work in progress limits. And can anyone guess how there was like a natural work in progress limit? We were putting Lego onto the manual, right? And there were only so many stages on the pages of the manual that you could put the Lego on until you flip the page, mixing all the Lego up again. So that was our natural work in progress limit. And using those whips, we swarmed around bottlenecks. So, we basically helped the people building if we run out of stuff that we needed to find. Tip number 7, limit work in progress and then pull more work from upstream if you're blocked. Always go upstream. So if you're a developer, help the testers out. If you're the BAs, help the developers out, etc. Time passed. And remarkably, in a pretty short period of time, after optimizing our system of Lego building using all these techniques from lean product development, essentially, we ended up building the finished thing. And at this point, I start to be able to use memes because it's 10 years later. Chewie, we're home! Hooray! Yeah, and that's what it looks like, the Millennium Falcon. There is a new one now, which is even bigger, but that's the Ultimate Collector's Edition Millennium Falcon from a decade ago. Unicorns and cats and things. So this, as I said at the start, this is my journey over a decade or more now. So I'm going to give you the conclusions from when I first put this talk together, and then we'll come back to them at the end with what I've learned since, potentially. So the first one is this idea of systems thinking, understanding the system that you're working in. And I think, especially as we get more experience, this becomes easier for us to do. When I was a very junior developer, I just wanted to be sitting writing code, right? Maybe with my pair. That's all I could get in my head because I was learning about how to do stuff. As we get more experienced, as we work in more teams over time, start to think about the system as a whole. Start to think about how we optimize the whole, not just what I'm doing. We talk in ThoughtWorks about how, as you progress from a graduate through to, grandfathered in director, people like me, how you should be thinking about influencing, what you should be thinking about at the different stages of your career. And as a grad, you're thinking about picking up user stories, understanding the basic tools that we've got in order to get stuff done. But then as you become a sort of more experienced, you maybe move to become a tech lead. As a tech lead, you should be thinking about the team as a whole. And as you become more experienced, going up to sort of staff engineer sort of level, you should be thinking about optimizing the whole thing and making sure that we take time to do that. That's the crucial thing. Time to think about the work and not just do the work. I was at a government department in the UK some years ago now, and I was talking with someone who's very senior, and we went through a really simple value stream mapping exercise. It took an afternoon. At the end of it, you had a whole bunch of stuff that you could go and sort of talk to teams about, optimizing and getting faster and so on. And that wasn't the important thing almost. At the end of it, he said, I just wish I had more time to do this more regularly. I wish I had more time to think about the work, not just do the work, not just be constantly firefighting. And I think that's a really crucial lesson. Understand the system and take time to think about the work and the system of work, not just doing the work. The next one, I'm sorry, I'm a bit passionate about that, can you tell? The next one is this idea of visualization. So visualization is absolutely key for so much stuff, right? Visualizing flow, visualizing cards going through your workflow, visualizing where requirements are coming from and where they're going to. You can use these really simple tools to visualize work. Kanban boards, story walls, I know we sort of have accepted them as sort of something that we just do. Often it's just, we just have a story wall. But what is it telling you? Story walls are so rich in information. They tell you where things are blocked. They tell you when your queues are growing, right? And going back to the lunch queue thing, just by looking at a storyboard, you get all this richness of information. And then you can turn that into things like cumulative flow diagrams, which means everyone can get a view of it. The next thing is this idea of continually working to identify constraints and working to remove or optimize away from those constraints. Another thing I've talked about is this idea of queuing work in progress limits, using these to visualize to help us understand where our bottlenecks are, right? Working to remove queues if we can. The ideal development process is single piece flow, right? The ideal development process is one thing moves all the way through the process without being blocked in any queuing state whatsoever. That is your optimal development process. But of course, it never works like that. We often have backlogs and so on. But how can we visualize those so we make sure that we're working to optimize the system by using these tools? And this idea of swarming as well. If my QAs, if our QAs are under the cosh, go and help them. It's no use just doing more stuff and handing it over, because all you're doing is adding work into a queue. It's not going to get into production anytime faster. It's just going to sit in a different queue, all right? So swarm, help your colleagues out, help other people on the team out. And then this idea of yesterday's weather and burn up, predicting the future based on the past. And finally, this idea of control charts for reducing variability. This is one of those things where, you did 30 points last week. Why have you only done 15 this week? That's just how it goes. That's just how the work slices up. That's just the system in which we're working. But it's a fair question to ask, why have you only done 2? And you should be asking that yourself. We should be understanding the normal levels of variability within our system. Right. 7, 8, 9. What I've learned since. Now, episode 7, 8, 9 with the subtitle of like 4, 5, and 6, but newer, which is pretty much as far as I can make out what they were. I'm not going to use Star Wars to illustrate this. I went and bought a different Lego set. This is the one and only time I've ever expensed Lego for work. But I did, which was great. And I expensed something called a Nexo Knight Lego set. Oh, hi. This is what it looks like. It's a big castle. 9 to 14. I didn't want to go for the collector's edition thing because, okay, it'd be taking the mickey a bit, right, to spend £500 on something for this. But I bought this set, which is a reasonably sized Lego set. And I want to ask the question to you in the room. If you were Lego and you were also constantly tinkering, learning from the experience of how people build your product, build Lego sets, right? What would be the change that would have the biggest impact on that system of work? Building Lego, finding bits, putting bits together. Sorry, making packages of stuff to find was the answer. So making packages of stuff to find. So if you remember when this set came out, basically they just bunched everything into one box. There was just 5,000 pieces in a single box, right? They were separated out into bags, but with no real ordering, no real structure to any of it. You just didn't know where to go to find stuff. It took a long time to do it. And what we did over time as we optimized our little process is we started creating little batches of things. Either batches in the sense of the pieces of Lego on the Lego page, or we started doing this just-in-time sort of inventory thing where we had these little cups. Back into a science bit. From the principles of product development flow, the batch size queuing principle. Reducing batch size reduces cycle time. Right. And if you take nothing away from this talk apart from this, I'll be absolutely delighted, absolutely delighted. Control batch size, and you directly control cycle time. By reducing the amount of work into small batches and delivering small batches through into production, we automatically get faster at doing it. There's this nice relationship, going back to these cumulative flow diagrams, if you like, between batch size, queue depth, and cycle time. I showed you this already, right? What you've got in this diagram is 2 big batches of work happening. Imagine you've got one deployment after 3 months, and then you have to wait again and deploy all the stuff you've built in 3 months, again 3 months later. You've got stuff that you've started working on, right, at the beginning of the 3 months. That's going to be sitting, waiting for deployment for ages, weeks and weeks and weeks and weeks and weeks, right? So the cycle time for that thing to get into production could be from 1 day up to 3 months worth. On average, it's going to be, what, 6 weeks. So you've got a cycle time for about 6 weeks. Just by reducing the batch size, you can go for a cycle time of like 6 weeks to a cycle time of days. Right? The work is still going into production, just in lots and lots of smaller batches. And this is exactly what continuous delivery is about. Because the smaller the batch size, the faster you get it into production, the less risks it's carrying. Right? It's closer to the people doing the work, so you're going to be able to fix any bugs more quickly because you've still got the context. Plus, crucially, it's going to make you more money. Right? Because something that goes into production there can be making money all that way versus having to wait and make money just that bit. So controlling batch size is the fundamental thing that is important about what we do. And that's why continuous delivery of software into production has been such a game changer and why the book has been so important. Don goes further. He says, batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization. You can shorten cycle time by orders of magnitude without adding people to your team or asking them to work harder. That sounds awesome, right? Batch size reduction principle. Queues have other problems as well, right? So the longer stuff sits in a queue waiting to be deployed or waiting to move on to the next stage, where you end up with a longer cycle times, but you also get this increased risk. Things might change. You get more variability, more overhead. You have to have more meetings to manage bigger queues and longer cycle times. You get lower quality and you get less motivated people. And to go back to the gentleman up there, it's exactly what Lego did. Lego basically moved to smaller batches. And if you've built any Lego with your kids, or like me, I'm an adult friend of Lego. That's a real thing, AFOL. I buy Lego myself. You can see that what happens now is they ship in these small bags. So for the first 10 pages, you use bag 1. You just have to sort through a much smaller amount. They've also done something else, and this is from Principles of Product Development Flow, which makes me happy on the basis of microservices and breaking big things up into smaller things, the fluidity principle. Loose coupling between product subsystems enables smaller batches. And that was one of the crucial goals behind microservices. By breaking things up into smaller bits that talk to one another, right, we can actually have more people working on them at once. We can improve our cycle time. We can reduce batch size that way. And that's what Lego have done as well. Many of their sets now are modular, so you can build bits of them in parallel if you've got enough people to do it. And then you plug them together afterwards. Ta-da, there's a next-gen-like castle being built. So let's revisit what I was saying as the conclusions from earlier. So I said visualize the system. Absolutely, but visualizing queues is probably the most important thing, or one of the most important things. Understanding queue depth and how queue depth relates to cycle time and batch size, super, super important. Identify constraints in your system, use the theory of constraints, but recognize its limitations in product development. The interesting thing with the theory of constraints is it assumes it's talking about machines. In general, machines can only do one thing. Humans are quite different to machines in the sense that we can do different things. Right? So the theory of constraints doesn't exactly apply. Exactly. If you think about that scouting story about the having to optimize for the slower scouts in the group to get there all at once. Don Ronaldson points out in Principles of Product Development Flow, again, that we could solve that problem in a different way. We don't have to have everyone get to the end of the high call at once. What you could do is say, have the experienced scouts go on ahead. They can start the fire. They can get a cup of tea brewing, if you're British, if you like a cup of tea after a hike. Right? They can gather firewood, all that sort of stuff. And then the rest of the scouts can follow along at their own pace. We can solve problems in different ways. Still worth understanding where constraints are, though. Still use work in progress limits and swarming to keep throughput high. And crucially, this idea of small batches directly impacting cycle time. By reducing batch size that we deliver through into production of our software, we make more money, save more lives, whatever it is you do, and that's the easiest way to do it. But you can only do that if you understand the system in which you're working, and I would argue visualize it and things. And then embrace anti-fragility, so the idea of fluidity principle, loose coupling, cohesion. I'm coming up to the end now. It's 5 minutes to beer, you'd be pleased to know. So I'll leave you with these books. These are the ones that sort of inspired me over the years and sort of inspired me to create this talk as well. So first is Principles of Product Development Flow, Building Microservices, Sam Newman, Continuous Delivery, and Lean Enterprise. I'll leave you with this thought, which is, software, what we do, what we're building, it should be cheap to replace, quick to scale, and resilient, and it should allow us to go, and this is the key thing, as fast as possible, right? Safely and sustainably reducing the lead time to thank you. We want to be going, improving flow as much as we can and going as fast as possible. So I would challenge you, in order to do that, ask yourself, what would Lego do? And they had the answer, they would use small batches. So thanks very much. Enjoy the rest of the conference, and thanks for coming.